speaking to us in the group. Welcome, my name is Banigbe. I am a public health physician and I will be facilitating this class this morning or this afternoon, this evening, wherever you are. Please, can you see my screen?
Yes, we can. Oh, yes, I can.
Okay, thank you very much, Dr. Usman. I'll just like to confirm that everyone received received a link to the R codes and the Excel file that we're using for this morning's class. What we've done in the past is, is that I would run the script and speak through the script while you also do the same on your own end. That way we can, in real time, troubleshoot if something is not working or if there's a need to talk through any set of steps. So this morning, we're going to run through the process of doing a meta-analysis using R. This is the R Markdown file that you received. To start, here's a link to a book that really takes you through the steps. This is a book, and you can take a look at it in your spare time. This is the first code chunk from row 19. Just helps you to clear your workspace. I am not going to run that because I already did this morning. So for this morning, what we're trying to do is to understand if media campaigns can increase consumption of 5 servings of fruits and vegetables a day. There is an Excel sheet that accompanies this that contains all the extracted data. Can someone just please let me know in the chat or just by unmuting themselves if you've received the Excel sheet and if you've taken a look at it?
Yes, we have.
Thank you. So, like you probably, if you remember from the recorded classes, one of the things that we said was when you're doing a meta-analysis, there are times that the authors of the primary papers don't report the exact effect size that you want. And you have to be able to find your way around calculating the effect size that you want using the data that's available. So the first part of this is just going to take us through how you can go from one effect size to another or calculate the effect sizes that you need. You will notice if you've had a chance to look at the Excel document, you will notice that all that has been calculated. And when we get to the point where we're using it, we're just really going to load it in. But the first like half of this class, we just go through how we do that by ourselves. So you can use the formulas that we've already shared in class, or you can use R. If you want to use R to calculate this effect sizes, you can use the regular EpiStats packages, or you can use the ELSCalc function in the meta-analysis package. What you do depends on you. So for now, we're going to use EpiR to create a 2x2 table. And here is a link to the documentation for the package. I'm sure you know that this, if you look at this next chunk of code, you'll see for row 51, there's a pound sign to make this inactive for me. But if you've never downloaded this package, if you've never installed it, just remove the pound sign so that you can install the package. So I am just going to call it up from my library using the library function. And then we will set up, this is going to be like manually setting up a 2x2 table. we're going to assign the 2 by 2 table to the object called ABOA 2021. And because we're trying to generate risk ratio, there's a particular format. Remember, like those 2 by 2 tables, exposure status on the left and then outcomes on top. So this is the exact format that you want to follow. So in this matrix, 297 is the number of cases among the exposed. 303 is the number of non-cases among the exposed. 123 is the number of cases among non-exposed, while 277 is the number of non-cases amongst the non-exposed. We're telling our n row equal to is telling our I want 2 rows, and by row we're telling our fill this matrix by row. The default in R is to fill by column, but we don't want that here because that's not going to work for us. So we're telling R to fill by row, and if you run this chunk, this is what you get. Please unmute yourself and stop me if you have a question or if there's something that's not working. So here is the classical 2 by 2 table that you use for this kind of analysis. And then the next thing is we want to calculate our effect sizes using commands from the APR package. Here, the options, the different methods in different EP methods, and so different methods in the APR package. So you can use the cohort.count, you can use the cohort.time, case.control, or cross.sectional. And this really talks about the design of the study from which your raw data came. So here we're going to try and assess, we're going to estimate the risk ratio. So we'll use a cohort.count because it's a cohort study. If you want to do estimate hazard ratio, you use cohort.time because it's risk over time. Case control studies, you will get odds ratio. So you use case.control. And for cross-sectional studies, you will either get the odds ratio or prevalence, depending on what you're doing. So another thing that we need to specify in our code is the outcomes. We want to tell R that we want the cases are column-wise. So our outcomes are coming from the columns. So here you install the packages. I already did, but if you need to install APR, then to install the packages APR, you load it, and here is your command. The rval is the object, and this is the command ep.2by2, and we tell it the data, our data file is ABOA 2021 that we set up here. And then the method is cohort.count, because it's a cohort study. Our confidence level is 0.95. Our outcome is by column. And then we want it, then once we set up this object, we tell R to summarize rval and to give us the associated details, including the risk ratio and the world, get the significance testing using the world method. So here is what we get. It's still working, I guess. So while mine is working, do we have any questions, comments? I cannot really see your pictures because I don't want it to cover in half of the screen. So if you want to speak, just go ahead and say something. Ojo A, are you trying to ask a question or contribute?
Sorry, can you explain what this MASOC detail and strata word are?
Okay, so here, this, right, row 83, line 83. So basically, you've assigned the object rval, you are asking R to summarize what is in here, and you want it to display the details, the association details. So the odds ratio. You also want it to show you the risk ratio, and you want it to give you want significance testing using Wald's method. So basically, you're asking it, this is what I want you to extract. Don't tell me every single thing in the background. I just want you to show me the association details, so like the estimate, and I want you to show me the p-value. Is this clear? Is it okay to move on?
Yes, please.
Okay, thank you, Dr. Kelechi. I think the easiest way would be to read this, to read the documentation that's highlighted in row 62, because then it tells you all the different commands and all the different arguments that you can include in this command. So I will move on. So basically for our val, what we've done is, excuse me, R has told us this is our estimate, this is the lower bound of the confidence interval, and this is the upper bound of the confidence interval. And so you can actually do a quick check to calculate the risk ratio by hand to ensure that you've set your 2x2 table correctly. So if you're doing this manually, if you didn't have the Excel document that the organizers of the class have generously provided, then you want to add it to your, once you get this estimate, the lower bound of 95% confidence interval and the upper bound, you want to add those to your extraction sheets. Does anybody want to quickly calculate the risk ratio by hand? Is anybody volunteering to do that? Okay, don't worry, I already did, and our table is set up correctly. So let's just move on. So here's another example, just basically setting up the table here. We're assigning the object is Adejare 2018, and we're telling R set up this matrix using the same, just don't forget, exposed case. So this is the format: exposed, the cases among the exposed, the non-cases among the exposed, the cases among the non-exposed, and the non-cases among the non-exposed. Similarly, so that's exactly what we're doing here. We're telling R in my 2x2 table, the 2 rows, of course, and then I want you to arrange this matrix or fill this matrix by row. Okay, so here is our object Adejare 2018 that we're setting up manually, and we're basically doing the same thing, asking R to using the APR package to set up a 2x2 table, and we're telling R here, this is our data, this is our data frame. We want cohort.count. We want this is the confidence level that we're setting, and the outcomes are in the column. And we're asking R to summarize, give us the associated details, the risk ratio, and including the Wald estimate. Toib, please go on.
Yes, thank you. My question is just to understand a bit why we are asking R to load the APR again. I think we just did, so yeah, just double checking why we are doing that again.
You're correct. There's no need, this is probably a copy and paste error. There is no need to load it again because we've loaded it once in this production. Thank you for pointing that out, Tori. Okay, so can we then run this? And And here's our estimate. This is the risk ratio, and this is the confidence interval for that risk ratio. We can do the same for odds ratio using the same Adejare 2018 matrix that we set up. And this time around, notice here's what's different. The method is no longer cohort.count. The method is now case.control, specifying to R that this is odds ratio. And if you also look at our command for the summary, it is now odds ratio, not risk ratio. So if you run it, you find here's the output. Is everybody following? So similar to, sorry, Esther?
You had the question. I said we are following you.
Oh, thank you very much, Esther. So forgive me, Olorunfemi Omobalade. Did you install EPR before you called it? Is it in your library?
No, it's not in my library currently. I'm trying to install it, but what I'm getting is error in library. There's no error in library, something like that. Error in install packages.
Really? So did you do I'm gonna put the the command in the chat. So basically install the packages EPR. Oh, thank you, Cheloka. I can see someone already gave you the code. Yeah, so if you do, so Cheloka already shared it. Thank you very much. So why don't you try that? Do install the packages to install it, then use library EPR to call it for this particular session.
All right, thank you. I'll try that.
Okay, thank you. Please let us know how it goes in the chat and if we need to troubleshoot a little more. Okay, so moving on, you can do exactly the same thing for hazard ratio or incidence rate ratio. And here, setting up your matrix exactly the same way. The method is now different. So this time around, the method is cohort.time. And when you ask R to summarize, you will use incident rate ratio .strata.wald. So that is the difference. So those are the differences if you want to use EPR to generate your effect estimate. Okay, so questions, comments at this point? Is everybody able to implement this on their end?
Hello?
Hello, Saliu. Yes, I can hear you.
My version is R console. It's not R EPR. That is my challenge here.
So you need to go to R Studio.
Okay.
You need to download R Studio, sorry, not go to R Studio. So first you need to download R Studio. And the best way to download R Studio is to go to the R CRAN.
Okay. I'll do that right away.
Okay, no problem. Olorunfemi, you're still getting the error. Would you like to share your screen? I'm going to stop sharing. Please share your screen. Let's see what.
All right, I'm trying to do that now.
Okay. You should be able to share your screen now. And ShareLocker is really providing input here. It says check your file. It may have been installed once, but just go ahead and check it, share your screen. Let's all see what's going on. And maybe it's something we can quickly solve. Are you having challenges sharing your screen? One or more of the packages to be updated are currently loaded. Okay, so why don't you follow the instruction here? Just to restart R.
Yeah, I've done that.
Okay, more of the package to be uploaded to be updated are currently loaded. Restarting R prior to install.
So it means that the APR is loading, is being installed. So he has to wait until it finishes.
Updating
Okay,
loaded
all right.
packages. Okay. Okay, so we will continue. Why don't you stop sharing your screen? We will move on. Give your computer time to load it, and then we can come back in a few minutes to see if you're still having challenges. Does that sound like a good plan?
Yeah, thank you.
Okay. So we'll continue from line 1 to 6. So basically, this is still just talking us through the different ways that we can manually or use R to calculate this effect estimates without necessarily, without using the meta-analysis package. So here, this time around, we're using the ESC package. I'm not going to go through the entire thing again because it's the same thing that we've done. It's just a different setup for using it. So for here, it's defining the data. You're assigning your so you're assigning the object A to the exposed among the cases, C to the unexposed cases, and treat, so number treated is the sample size of the treatment group, while N control is the sample size of the control group. So the first thing you're going to do, of course, is to calculate the risk in each group. Then you calculate the risk ratio. So if you look at it, it's very similar to what we got earlier. And you can, so let's assume that you were manually extracting the data from the primary studies. You can set this thing up. So this is for one study. You can get the risk ratio, you can get the log of the risk ratio, and you can get the standard error of the log of the risk ratio. So here is the log, and here is the standard error of a log of the risk ratio. And if you were going to, if you want to do the same thing for to calculate the odds ratio, using the ESC package, you have to call it out of your library, and then you have to set it up. And you have these definitions of what goes into group 1, yes, group 1, no, group 2, yes, group 2, no. And here is the command that you use, the ESC underscore 2x2. You define your groups, and then you tell it the type of estimate that you want. Here it's odds ratio, and if you run it, then you get your output. And so here is your output, tells you the effect size, the standard error, the variance, all the things that you need. You can also calculate the log odds ratio by setting the ES type to logit. And you can see similar command, similar group setup, except that this time around the effect size type is logit. And it tells you the log odds of the odds ratio. Doing the same thing for incidence rate ratio. This is how you set up your data. This is how you call it. This is how you calculate the incidence rate ratio. This is how you calculate the log of the incidence rate ratio, and then its standard error. So I'm just going to give 1 minute. Olorunfemi Omobolade, Sarah has a suggestion for you in the chat. Please check it out and let's know if it works. Thank you, Sarah. Is everybody at this level? Is it okay to move on? Are there questions? I will be looking in the chat from time to time. Olorunfemi, let us know how it goes. Okay, so we will then go on and talk about how to use the ESCalc package to do the same type of analysis. When we used EPR, one thing you will notice is that we had to set it up. We had to set the command up for each study. So we set it up for individual studies. If we want to do it everything at once, we can use the ESCalc. And the first thing to do will be to import your data set, the Microsoft Excel document that you received, import it into R. And these are just libraries that you can call up. Read Excel will help you to import your Excel file into our dplyr. It's a data wrangling package. So this is a command to import your Microsoft Excel document, and you're basically saying, this is the name that I'm assigning to it in R, bring it in. This is its name, and I want to import the data in sheet 1. It has column names. The data type is null, and then these are the other arguments in the command. So can we import our data? Please let me know if the challenges at this point.
Sorry, why are you doing the entire sheet 1 column type, column names? Is it not just for us to import the data just like that? Why do we need to do the rest?
So you want to specify, depending on the type of data, depending on the way that you set up your data, you're basically telling it, does it have column names? Yes. So you have headings, right? Hello?
Yeah.
Yes. So sometimes you set up your data and you set up your Excel sheet and it's just numbers. There are no headers or descriptors. So you tell it, no, it doesn't have column names. And here it's just like telling you or showing you all the different arguments that can go with read Excel. So for instance, you wanted to skip any. What is the maximum number? It's infinite. Each name is unique. So basically, I think the short answer is read the documentation that comes with the read Excel package. It shows you all the different arguments. In reality, you may not need to use every single argument every time you import data, but it's good to know them, especially if you're not the one that set up the Excel document. Does it answer your question?
Yes, it does. Thank you.
Okay, so excuse me. So we've imported our Excel document, and the different measures in the ES-Calc that we can use. We have, for the measure arguments, you can use RR for risk ratio. Please mute yourself if you're not speaking to us. Thank you. RR for the log risk ratio, OR for the log odds ratio, RD for the risk difference, PITO if you estimated the log odds ratio using the PITO's method. So basically, these are the options that are available to you. And here we're just trying to recalculate some of the risk ratios we already have. This is just an exercise, right? So we've please note, you have to install Metafor, the package Metafor. I already installed it, that's why it's commented out here. So install the Metafor package, then call it up in your library. Let's set up the data frame. We're going to use the command ES-Calc, and we're telling our, we're telling R that the measure we're calculating is the log risk ratio. This is the way to set it up. See the instruction here. See the instructions in lines 226 to 228. But basically, these are headers in our Microsoft Excel sheet. Okay, great, Femi. I hope you catch up with us. So these are headers in our Microsoft Excel sheet. Remember, this is the name of our of the data frame that we imported, and then this is a column name. So we're saying basically NLI is the number that's exposed. AI is the cases among the exposed. BI is the non-cases among the exposed, just like here, basically, right? These are the arguments that the ES-Calc takes. So we're basically telling our NLI is this. When you're looking for NLI, go look in my imported file and look at and take data from this column. Take data from this column, okay? And then the variables that we're trying to generate, YI and VI, and then the data, we're basically saying the name of my data frame is the media veg.dat, which is what we named our Excel document when we imported it. So don't ignore my error messages. I'm just not ready to go to the higher version of R yet. Okay, so to confirm that, so basically in this DF, what we've done is that we've calculated the log odds ratio again. And then to confirm that the numbers are correct, just subset and view the old log effect size and your new column YI. Can you see we assigned I to it, and we basically said subset it, look in the DF, select log ES, which is the log of the effect size in the Excel document, and YI, which is what we just calculated. Same thing here, the risk ratio. And I'm just going to, can you see it? So this is what you have. log ES is what you have in the original Microsoft Excel document, and YI is what you calculated by yourself using the ES calc. And can you see that it's the same? So basically, this is just an exercise to show you how that you can use ES calc to calculate all the effect sizes that you need at once. And it's exactly the same thing as what was, manually extracted from the primary studies in the Microsoft Excel document that you received. And ES calc is slightly different, or if you like, better than using the EPR, because for EPR, we're basically calculating it we're setting it up for individual primary trial, but with the ES calc, we just put in everything at once, and here we are. So comments, questions, thoughts?
Hello, good evening, ma.
Hi.
I'm fine, ma. Thank you very much for your presentation. I just came late because I'm so busy in the office. I'm just joining the chat now. I missed from the beginning, but maybe I'll watch the lecture after presentation. Thank you very much for it.
Yeah, thank you very much, Labaran. So I'll just say that what we're trying to do, what this class is trying to do is like run us through the process of doing a meta-analysis using R. And you received a Microsoft Excel document that already extracted information from the primary studies, including the effect sizes and the log of the effect sizes. And we've spent the last like 40 minutes just going through different methods that you can use to also generate those exact effect sizes from using R. If, for instance, the authors of the primary studies did not report exactly what you want. So at this point, we've basically just shown that there are two packages we can use, the EPR and the ES calc, and we've demonstrated both. Okay, so now we're going to start meta-analysis in Metafor. So just let's read through this. We already have that. Create your data. So if you're going to use Metafor, you have to create your data sheet in Excel, and your first row should have headings. We already did that. The code chunk below is the one that runs the main meta-analysis, and it will produce the forest plots to run the models that you have calculated. You have to log transform the relative risk. And the key decision, as you've learned from the recorded classes, is whether you want to use a fixed effect or a random effects model. YI is your effect size. The
This class, I'm not understanding, but let me get out of it.
Is Samira still here? Okay, so we'll continue. If there are questions, please ask questions. I'm happy to go over stuff. So just going back to the beginning of this, we're going to run our meta-analysis in Metafor now. To do that, you have to create your Excel datasheet, which has already been created for us. And this, the next code chunk is going to run the main meta-analysis, produce your forest plot also. And the key decision is whether you want to run a fixed effect or a random effect model. Does anybody remember the differences between fixed effect and random effects model? And if anybody wants to quickly share with us?
Hi, I can try, Dr. Bola.
Yes, please.
Yeah, so in the fixed effect, I think the assumption is that the studies you want to use in your meta-analysis it's as you assume they like have, let me say, the same study size, they're conducting the same location and things like that. But it's always advisable to go for the random effects because obviously studies like done like in different areas, different geographical locations. The patient or the client you recruit in these studies also will vary, and it has a way of impacting the study outcomes in the long run. So I think that's the rationale behind the fixed or random effects.
Thank you very much, Adeze. I think that is a fair shot. Like you said, the fixed effects, using a fixed effects model assumes that all your primary studies, they are assessing the same underlying concept or the same underlying effect in the population. Abang Umar, please. Your hand is raised. You want to ask a question?
I wanted to give a suggestion too on the fixed and random effect model. I don't know if I can go ahead.
Yes, please.
All right. I think the fixed and the random, the choice of fixed and the random effect model is based on the exposure and outcome relationship. Okay, that's when we use either the fixed or the random effect model. If the exposure outcome relationship are the same, we go for the fixed, and if they are different, okay, we go for the random effect model. That is, if the exposure and the outcome we assess in the exact same way across the studies, we go for the fixed, and then if they are different, we go for the random effect model.
Thank you very much for your contribution. Yes, if based on your understanding of the primary studies, you think that the relationship between the exposure and the outcome variables were assessed in the same way, and like Adeze mentioned also, if you think that the population is the same, the studies were conducted in the same way, and the underlying causal effect that the studies are measuring are exactly the same, then you go for a fixed effect model. But if you're not sure, or if you know it's by reading the primary studies, you're like, oh, not exactly the same. Maybe the instrumentation was different. Maybe the definitions were different. Maybe the age groups, maybe the geographies were different. And you're like, I cannot particularly say that these are exactly the same population. Then it is advisable to go for the random effect model. Thank you very much for your contributions, two of you. Okay, so let's assume that we've made a decision. Yes, Labaran.
Yes, another solution on effect, fixed effect and the random effect. Sometimes we are assuming that when you say fixed effect model, we assume that the individual specific effect is correlated to independent variable, while the random effect allow us to make inference on the population given to us.
Could you explain a little more? I just want to be sure that I completely understand what you're saying.
What I'm saying that sometimes when we say effect, fixed effect model, well, we assume that the individual is correlated to independent variable, while the random effect model allow making to inference on the population given to us. I don't know whether it's making sense.
Yeah, okay, so do you mean that with fixed effects model, our inferences are limited to the primary studies, while for random model, we can take those inferences and generalize beyond those studies that are in our meta-analysis?
Exactly.
Thank you, Labaran. You're right. Okay. Thank you for this contribution. Okay. Nuru Solomon, do you have a question or a comment? You can just unmute yourself if that's possible where you are. Otherwise, I will continue with the class and keep checking on the chat for when your question comes in. Okay, no problem. Thank you, Nero. Okay, so Packard wants me to explain why we chose the log of the effect sizes. We usually log transform in situations where not every effect size from the primary studies is normally distributed. Is it clear? Would you like me? Okay, Sakat. I'm sorry. I feel like I just murdered your name. Please forgive me. Okay. So please mute yourself if you're not speaking to the class. I will just go on now. So I'm going to assume that you've already decided based on your understanding of the subject area, based on your understanding of the primary studies, which of the approaches you want to use. So in Metafor, yi is the effect size. And then the log of the standard error is the natural log of the effect size. And then you can also use variance instead. Instead of a standard error, you can use variance. And then measure, when you specify the measure, it tells R which measure you're using. In this case, it is log of the risk ratio. So this is what the code looks like. So you call your library, you call the Metafor package using the library function, and then you assign a name to it. So the command is the RMA. Your yi, remember, that's the effect size. So you're telling R, my effect size, the effect size that I want to use is the log of the effect size. And then the standard error is the log of the standard error of the effect size. My method is FE, fixed effect. The measure that I'm using is risk ratio. And this is a data frame. This is the name of the data frame that I am going to use. And then you tell R here to summarize this model. So let's run that. Great, this is what it tells us. Are we all here? Does everybody have this? Because this is the meta-analysis, right? So is there anybody who's not at this point yet? I'm going to assume then that everybody is following. Does anybody want to volunteer to tell? Okay, thank you, Mukhtar. Does anybody want to volunteer to tell us what does this mean? You know, it's one thing to run the code, but as researchers, then we have to explain what it means. So does anybody want to explain what this output means? Let me tell you something funny. In my classes, I volunteer people. I don't always wait for people to volunteer themselves. So is there anybody that wants to volunteer themselves, or should I volunteer somebody to explain?
Let me volunteer.
Thank you.
Yeah, this is a study, a 13 different study. The p-value is 0.001, which is significant, and there is a considerable homogeneity, which means 85%, showing that the study is considerable difference amongst themselves. There's randomness within the study, there's variation. So, and we look at the effect estimate is 0.003, the standard error 0.0255, and then we have the val, z-val 12.96, the p-val 0.0001, and that's what I can deduce from the study, and it's a fixed effect model that we applied.
Thank you very much, Sheloka. Before I comment on your input, I see that Mfong raised their hand.
Oh, all right. Okay. Going for that, I can see that the effect estimate, the pooled estimate is 0.33 with the upper confidence interval of 0.3799 and the lower confidence interval, the lower boundary is 0.2801, which is at the right of the null line of null effects, at the right of 0. I think that's what I can see too.
Thank you very much, both of you, for contributing, and your contributions are correct. So I'll start from the top here and say it tells you this is a fixed effects model and there are 13 primary studies. Then let's look at the I-squared. I-squared is basically a measure of heterogeneity between study heterogeneity. And like Sheloka said, it's pretty high here, 85.34%. So basically it's telling you a lot of the variance in your effect estimate is due to the differences between the studies, not within study estimate. And it's basically, this is your Cochrane's Q test for heterogeneity, same. We don't really go for the p-value of Cochrane's Q. But generally people will just stay with the I-squared. This is your model result, which is like the meta-analysis itself. And like they both said, your effect estimate is 0.33. Its standard error is pretty small. And you can see here the upper and lower bounds of the 95% confidence interval. The p-value is less than 0.0001, which is significant. And your confidence interval, your 95% confidence interval tells the same story, because the 95% confidence interval does not contain 0. So you're like, okay, there's a significant, the effect estimate just shows that there's a significant difference between whatever groups we're comparing here, right? So that is something similar to that is what I would write if I were, like reporting the results of this meta-analysis. Do we have comments, questions, additional thoughts? Okay, so if there are no additional thoughts, I'll just go on. I will comment this out. This is a similar command, but using a different data frame. Here we were using the data that we imported, the Excel data that we imported. Here is a different data. Please mute yourself if you're not speaking to us. And I'm just going to run this. And you can see that it's the same thing, but this is from the data, where's GF? The data frame that we set up earlier using this is the data frame that was set up earlier. So basically it's just showing you another way of running your meta-analysis using the Metafor. So before we go on to forest plot, are there thoughts, questions, comments?
Excuse me.
Yes.
Please,
yes.
Please, will it be possible to show us the exercise 284 with a random model method. Because what we did was, yes.
Oh, okay. Yeah, we do have it. Just keep breathing. We'll get there in a few minutes. So thank you, Cheloka. Before we go on to random effects, let's just do the forest plot for the fixed effect. And first, we're going to ask R to sort the studies using author year, right? And then we're going to use the forest command. We specify the name of the model that we're plotting. We tell it the reference line is 1 because it's a risk ratio, right? And then this is the label SLAB. This is the label that we want on the forest plot. And we're basically we're telling it the limits, like of the effect sizes on the x-axis. I don't remember what CX is. I'll remember when I remember. I'll come back to it. I don't remember what this argument is right now, but when I remember, I'll come back to it. So basically, this is how we specify the forest plot, right? And here is what we have. Is everybody able to get the forest plot for the fixed effect model? As you can see here, it tells you this is the fixed effect model. This is the fixed effect estimate, and it's on the right of the line of no effect or the reference line. And as you can see, the size of the boxes correspond to the precision. And so the precision of the studies, the weight assigned to the study here. And so you can see also the 95% for the bigger boxes, their wings, the 95% confidence interval is shorter compared to, say, a study like this one that is small. The weight is small and its 95% confidence interval is wide. So what do we say? Does anybody want to take a stab at interpreting this forest plot or this, fixed effect model? Yes. Mfonobong. Please tell me, is that how to pronounce your name?
Yeah, you're right. You're right. Mfonobong.
Okay, thank you. I don't like to murder people's names. I'm sorry.
It's no problem. Okay, to interpret these, there are about 13 studies here, and we are using the fixed effect model. The line of null effect, okay, which crosses runs through 1 in the x-axis. And looking closely, of course, you can see the plot from R does not give the individual weights, okay? But looking at the studies, looking at the size of the boxes, you can see that the second study has the highest weight, okay, contributes more in terms of the sample size to the studies, to the meta-analysis, followed by maybe the third or the fourth study. But it is clear that the second study has the highest weight. And yeah, now I'm going to the diamond there, down there. The width of the diamond is the pull effect, where that diamond falls is at 1.39, right of the line of null effect. And it is statistically significant. The pull effect, the pull estimate is statistically significant because it does not cross the line of the null effect. And the confidence interval runs from 1.32 to 1.46. Statistically significant. That is it.
Thank you very much. I agree with your submission. Thoughts, additions, questions about the forest plot before we move on? I'm so sorry, Abraham, for you having connection challenges, but this has been recorded and it will be available. And of course, there's still other opportunities for live sessions. So if there are questions, there are opportunities to ask questions. So now we'll go on to talk about random effects. And we're going to be doing the random effects model using the pre-calculated effect sizes that we have in the Excel document. Okay, I see your question on explaining the boxes. We still have one more, we still have a few more forest plots coming up. So I will take time to go over those boxes then. How to transfer the box plots to a Word document. You can save. Can you see this? Can you see this neat function or the button, whatever? Can you see the neat? If you knit it, you can knit it to Word, to PDF, or to HTML. So the knitting is almost like, knitting, converting the outcomes or the results into one document, basically. Okay. Yes, you're right. I think there you're right. There must be a mix-up. I see also that the effect estimates 0.33 and 1.39 are not the same. And I will investigate, but the command is correct. Let's just say that. So it's not the command that's the problem. Where were we? Okay, so let's talk about random effects. So basically, we've decided what we're going to do. We're going to do a random effects model, and we've specified it here. And we're using the RMA command. Our YI is the log odds of the effect sizes. SEI is the standard log of the standard error. And our method is the REMO, random, the maximum likelihood. Our measure is risk ratio, and this is the data that we're going to use. Okay, so let's run this. And this is the command for the forest plot. Basically, we're telling it to use the random effects, to plot the random effects model. So let's start with the output. Similar. So it's basically telling us there are 13 methods. And because we've told it that this is a random effect model, it basically calculates the tau estimate for us. And it's estimated, the tau squared is the estimated amount of total heterogeneity. Because we've specified that it is random effect, it agrees with us that the heterogeneity is high. You can see here the effect estimate is slightly higher than what we got from the fixed effect model, but the conclusions are the same. And here is the, I see what Awa was saying about the effect sizes. The effect estimates are not the same in the forest plot and in the random effects model. I see. We have to investigate that. But basically, let's just say the what's it called? The commands are correct. It must be something about the data frame itself. The commands are correct. And our interpretation, of course, does not depend, our interpretation of what's significant and what's not significant, the meaning of the different outputs of the outputs are the same. So whether it's 0.37 or whether it's 1.46, the estimate is still what R means by estimate is the pooled effect, the p-value, and what's it called? The confidence intervals are the same. So looking at this, let's talk about the boxes again. So here, this is the first plot. On the left side are the studies that have been used. 1, 2, 3, 4, 5. Okay, these 13 studies, right? The 13 primary studies. And you can see for each of the studies, we have the effect estimate. We have the effect estimate that is at the center of these boxes. So the effect estimate is at the center of the box. So for Abioye 2021, the effect estimate is somewhere around, let's say, 1.6, thereabouts. And the wings of the boxes represent the 95% confidence interval around that estimate. So the effect estimate for Abioye 2021 is 1.61, and the 95% confidence interval is 1.36 to 1.9. And you can see here for Adebi 2018, the effect estimate is 1.09. But can you see how narrow the 95% confidence interval is? The width of the confidence interval is a measure of the precision of the study. So if it's like a wide 95% confidence interval, it is less precise than a study that has a narrow confidence interval. So what happens in meta-analysis, these methods, they assign a higher weight to the more precise studies in calculating the pooled estimate, or this diamond. How we can tell visually which of the studies have higher weights is by the size of the boxes. So you can see, for instance, comparing Adebi 2018 study, that's the second study, with the KK 2007 study. Look at the size of this box. It's very small compared to the second one. And if you look at the width of the 95% confidence interval for the KK 2007 study, it's pretty wide. It actually crosses 0. It contains 0. So it's less precise than, say, this study, this Adebi 2018 study. And because it is less precise, the rectangle, the size of the rectangle, the area of the rectangle is smaller. So is it clear? Someone wanted me to go over what the boxes are. Is it clear? Okay, I'm just going to go on. And if there are other questions, please let me know. Thank you, Sarah, for that explanation about the difference between the estimates in the forest plots and in the output. Okay, so where were we? Okay, so now we've talked about fixed effects model and random effects model. Is it clear? Everything okay? Can we move on to talk about publication bias? Okay, so to talk about, okay, thank you. Publication bias Okay, publication bias, there's like a visual way of looking at it. And publication bias is just this thing about, in some instances, people are generally more likely to publish studies where they found positive, significant outcomes than negative outcomes. There's that positive outcome bias in publication. There's also the bias of people are likely to publish results of large studies than small studies, especially when the small studies have negative, don't have like a non-significant outcome and all of that. But in a meta-analysis, we're really thinking about, in a meta-analysis, we're really thinking about the universe of all the studies that are out there. We are not just interested in studies that had like favorable outcomes. We're talking, we would ideally be liking to look at every study, whether the outcome was favorable to this hypothesis or not. How do we know? How do we begin to assess and get to that point of whether, there's something missing or something, if there's something missing in this body of knowledge or this body of publication? We can use the visual method using the funnel plot, which basically just helps us to look at symmetry or asymmetry. And then we can use almost like, like a regression test to statistically determine whether the funnel plot is symmetric or not. So here is the command. This is our random effect model that we set up here. And we're just basically saying, can you plot the funnel plot for this random effect model? And then the statistical test to test the symmetry or asymmetry of the funnel plot is a regression-based test. So we're basically asking R to do that for the random effect model. So let's do that. So here is our forest plot. Any thoughts about this forest plot? If this was your meta-analysis, how would you report this, or what kind of impressions would you form from this? Mfanaba?
All right, the forest plot looked clearly symmetrical. Okay, from what I'm seeing. Looking at the triangle, equal number of studies seems to be on the right hand side. Okay, at the middle of the triangle, maybe drawing a line from the at the middle of the triangle, equal number of studies seem to be on both sides of the line. So I think it's symmetrical.
You think it's symmetrical? Thank you, Mfanaba. Anybody thinks otherwise? So do we all think this is a symmetrical funnel plot that does not appear to be, we don't get the sense that maybe any studies are missing? Okay. So I say it's...
Hello?
Yes, please, Salio.
Hello?
Hello,
Yeah,
go on.
this studies is symmetrical because the line at the middle of the triangle, that is the line of no effect. Then by the right, you see that is at the positive angle of estimates, full estimate, and then the one by the other at the left, that is at the minus level. So it's
you mean this one?
Yeah, that is the at the negative side of the plots. So it's not symmetrical at all. It's symmetrical based on my observation.
Yeah, I'm leaning towards the symmetrical too, like I'm asking, you know, like, where's the corresponding study? There should be, you know, like, I would have loved to see a corresponding study, you know, like a small study with a positive effect. And it looks like, if you look at this side, it looks like there should be some studies here. So let's assume that myself, Saliu, and Mfonobong are on the same research team.
Yeah.
Let's assume that we're on the same research team. How are we going to, please mute yourself. How are we going to, so what are we going to do? What are we going to report? It is like, what are we going to report? Two of us think it's asymmetrical. So one team member thinks it's symmetrical. It is in instances like that, let me not say instances like that. The statistical test can help us to determine whether there's symmetry or asymmetry. So here, remember this reg test, the regression test for the random effects model is helping us to statistically determine whether the funnel plot is symmetrical or not, so that we are not scratching our heads and deciding, you know, like, here is the output for the regression test. Any thoughts about how you would interpret this?
I think from the outcome of the funnel plus symmetry, we know that when the p-value is greater than 0.5, then there is no publication bias. But from this outcome, the p-value is greater than 0.9518, which means there is no publication bias. Then the outcome is symmetrical, and we have the confidence interval between 0.129 to 0.6299.
Yeah, thank you very much, Chiluka. So basically, here is the result of our test for plot asymmetry. This is the Z value, and the P value is 0.9518. As Chiluka said, it's much, much greater than 0.05. So we can say there is no asymmetry. And the confidence interval of our plot estimate also tells the same story because it does not contain 0. Adetola Babalala, please.
Thank you very much, Ma. I just want to ask a question based on the prep plots. If you can go back to it, there seems to be an outlier. Yes, there seems to be an outlier to the left, a study below.
This one.
So,
oops. This one.
No, yes. How can we interpret it? What is wrong there?
Sincerely, I won't say there's anything wrong, right? We have to go back to that study, to the primary study, and see how the study was conducted. And remember, if you look at the standard error, which is a measure of the precision, starting from 0.36 all the way to 0. So as you go up, as you go up, the precision increases. Larger studies tend to be higher up, and the smaller studies are at the bottom. So this is a small study that had this, that found this outcome. I won't say there's something wrong. It is just what it is. We'll go back to the primary study and see if we extracted it correctly, if there's something about the design of that study that that made it look like that. And sometimes it is just what it is. I won't say there's something wrong with the study. Mfonobong?
Responding to that question, I think you're right. It is what it is. Why we have that outlier is because maybe since that particular axis is for the standard error, maybe the sample size of the study was very, very small because we observe we have the sample size of a study being small, the standard error actually increases. So it might be the factor of the sample size of that study. But I think when we are looking at the symmetry, we are just looking at the left and the right-hand side of the line in that triangle.
Yeah, thank you for your contribution. Adetola, any thoughts? What do you think?
Thank you very much. Clearly understood.
Okay, thank you. And but personally, I prefer this statistical test because I'm usually getting into arguments with people like, no, not symmetrical. So I guess it's always like another layer of comfort or another layer of confidence to do the regression test for asymmetry. So sometimes there is publication bias and our funnel plot is asymmetrical. We can use a method or a technique called the trim and fill to guess how many papers are missing and what their estimates would look like. Remember, this is a guess. This is an informed, uneducated guess. So it's not like when you're done, you now go and look for, it's not like you have to go back into the literature and look for the 10 additional papers that should have been there. It's just basically saying, let's take a look at it. If there was no publication bias, what will this model look like, or what will this funnel plot look like? And one of my favorite statistics saying is every model is wrong. It's not like this one. So how do you do that? Is using the trim. So you can use a trim and fill for the model. And let's see what it tells us. So basically, it's telling us that if there was no publication bias, this is what the effect estimate would be. And if you go back to the random effects model, where is it that we generated? Our pooled estimate is 1.46, right? And here, using the trim and fill, it's saying the same thing. So it basically almost goes back to that, to what some of our colleagues have said here, that there's no asymmetry in this particular study. And the regression test also tells us that there's no asymmetry. So, and here, this trim and fill model is telling us, even if you go, let's model what it would look like. What would be different if you found publication that's missing? It will still be 1.46.
In fact, Ike Wolo, I really don't know why.
Please mute yourself. Thank you. So questions, comments at this point, So at this point, we're done with the meta-analysis. We've gone through how to get our, please mute yourself. We've gone through how to get our effect estimate. We've gone through how to get our effect estimate using two different approaches. We've used Metafor to generate our pooled estimates, the forest plots that go with that, the funnel plot, and the regression test for asymmetry. We tested the trim and fill model to guess how many papers are missing and what their estimate would look like. The rest of this is just using another package to do our meta-analysis instead of Metafor. So Meta is another R package that we can use. And to do that, we need to call, assuming that you've installed Meta, we need to call, assuming you've installed Meta, you need to call it up in your library. You need to call tidyverse and a companion package for Meta called the dmeta. So that's what I am doing right now. Okay, so we can either use the raw data that we generate by ourselves, or we can use the pre-calculated effect that is in the that is in the Excel sheet that we have. So when you're using the raw data, you have to specify exactly what method should be used. Should it be the inverse variance pooling? Do you want the Mantel-Hansel method, or do you want the Peto method? You have to decide which of the approaches you're using, fixed effect or random effect. In Meta, both methods come in the argument. So one has to be true and one has to be false. And then you have to indicate what you're interested in, whether it's a risk ratio or odds ratio, and then you want to decide whether you want the exact continuity correction or not. Basically, you decide what all the arguments are, and this is what your code will look like. Remember, events, the same way that you will set up a 2x2 table, basically. The cases among the exposed, the number of exposed, the cases among the unexposed, the number unexposed, and then what do you want? The study label, how you want the y-axis of the forest plot to be labeled, the data that you're going to use, the measure that you're going to use, what method, whether you want continuity correction, whether if the meta-analysis approach, whether it is fixed effect or random effect, and then the title, then the other specifications. And when you run it, you then get something like this. And this is your risk ratio. This is the pooled effect. This is the 95% confidence interval. This is the p-value, very similar. So basically we're getting very similar. The numbers are slightly different, 85.4 earlier, 85.3, but we're getting very similar outputs. And this is when you do this using the raw data that you set up yourself. Or you can just use pre-calculated effects like what you have in the Excel sheet. And basically these are the comments. We've discussed them earlier. And it gives you, like same output depending on where your data is coming from, right? Forest plots in Meta is a bit more flexible, and you can be a bit more fancy. So you can ask the risk of bias variable. You can add different things. You can even specify the format that it will come out. So this is the study and the author. This is your log. This is a log of the risk ratio and all of that. This is the weight. So you can add more things to your forest plot. Also, you can specify the different types of layouts. So here's a layout called RevMan. Don't ask me why it's called RevMan. I don't know, but it looks prettier. And here's a layout called JAMA. There's some publications or some journals that have their own preferred layout. So this is probably Journal of the American Medical Association preferred layout. So you can see, for instance, different. So if you know, for instance, that you're submitting to JAMA, this would be a good layout to choose so that it's already formatted for that journal. So basically, you can explore, you can just read the documentation that comes with Meta and the forest plots to see what other layouts are available and if there's stuff that you will find useful. We have come to the end of our codes. We have a few more minutes before 11:45, my time. Thoughts, questions, comments, ideas are welcome. I'm going to stop sharing my screen now. Thank you, Mariam. Please install our studio, watch the recording, and if there are questions, you can reach out before the next session, or if you think the questions can wait, then we'll definitely take them during the next session. John, to clarify, the funnel plot helps you to know if the published data are skewed to one side. No, it helps you to see if there's publication bias. So the bias is not about the result in the primary studies that you've extracted. It's more about, do you think there's something, is there a possibility that something is missing in the data, in the studies that have been published? So is it possible, for instance, that some people, maybe they did their study, they found something that was not significant? You know, there's a school of thought out there that when people, when trials are not significant, you know, non-significant findings, people are generally less likely to publish them. But what it means then is that if we don't publish all the non-significant findings and we keep pushing out only the significant findings, can make some interventions look more, it can make some interventions look more effective than they are. Because if 10 out of 15 publications about a particular intervention say, oh, this intervention works, it looks like it works, but what if there's, you know, like maybe another 7 or 8 experiments or studies that found that intervention didn't have a significant effect and they did not publish. So that's the whole idea of the funnel plot. The forest plot, I will go back, share my screen. So the forest plot, here, one forest plot. So the forest plot is basically a visual representation of the studies in the meta-analysis, their effect estimates, and the common effect or the pooled effect. I'm actually going to go to a less, that other funnel plot that I showed earlier is just unwieldy. This is easier on the eyes. Okay, so these are the studies and these are the author names and the year. This, I will start by looking at the individual study. The box or the solid black rectangular box represents the effect estimate for this particular study. So for Abioye 2021, for instance, the risk ratio is 1.61. The line around the box represents the 95% confidence interval of the effect estimate for that study. So for Abiri 2021, the 95% confidence interval is 1.36 to 1.90. And if you look at Adebi 2018, the effect estimate, the risk ratio in that particular study is 1.09, and the 95% confidence interval around the risk ratio is 0.99 to 1.2. The same for all the other studies, right? Now, the relative size of these boxes corresponds to the weight assigned to the study in this meta-analysis. And the weight is an inverse. Remember that the most common approach to meta-analysis is called the inverse variance. It's an inverse of the 95% confidence interval. The more precise studies are assigned higher weight. So for instance, look at the 95% confidence interval of Adebi 2018, is 0.99 to 1.0, very short. Compare that to the 95% confidence interval of KK 2007, which is 0.83 to 2.21. It's wide. Because the 95% confidence interval is wide, it means that the effect estimate is less precise. And so it is assigned a smaller weight compared to the studies with shorter 95% confidence interval. So that is the whole idea of the size of the rectangular boxes and their weight to in the weight that's they're assigned in the meta-analysis. This diamond is the pooled effect across all the 13 studies that we're using in this meta-analysis. And you can see the center of the diamond is the pooled effect estimate, 1.46. The wings of the diamond are the 95% confidence interval bounds of the pooled effect estimate, in this case, 1.28 to 1.66. Because this is a risk ratio, or because this is a ratio, so if it's whether it's a risk ratio or odds ratio or incidence rate ratio, because it is a ratio of 1 means there's no difference between the two groups that we're comparing. That is why our line of no effect is at 1. So the line of no effect is at 1. Anything to the left of the line of no effect means there's a negative effect. To the right of the line of no effect means there's a positive effect. So you can see that, some of our studies, they cross the line of no effect. So we'll say there's no significant difference between the groups in those primary studies. But for our pooled estimate, it is nicely on the right side of the line of no effect, suggesting that people who were exposed to the intervention had, more of the outcome that we were studying than people who were not. I hope this is clear. Please send me an email if you still have questions. Sarah, you couldn't find the DMeta package. What version of R are you using? The DMeta package was developed in 4.2.2. As you can see, I've also refused to upgrade to 4.2.2, so I don't have it either. But if you upgrade to 4.2.2, you're likely to be able to download it. Thank you, everyone, for your time. It's now 11:45 on my side of the world. If there are no additional questions, I will stop recording.